Hi everybody, my name is Farnaz and I'm going to be running through exam 1 of 2012 for organic chemistry. This is my very first instructional video, so please bear with me if things get a little out of hand with technical difficulties. So in the first question we are going to be looking at this molecule Lipitor, and we're going to try to identify the functional groups. Now if we look here, we have a functional group alcohol, and we all know, hopefully by now, what an alcohol is. And if we look in here, we have two alcohols. Now next we're going to try to find an amide. An amide is there is a distinct difference between an amide and an amine. An amide has this nifty little thing attached to it. And these hydrogens can also be R groups. And if we look, we have an amide right over there. And next we have a ketone. Now ketone falls under a group called carbonyls. And there are two types of carbonyls. There are ketones and there are aldehydes. There is a very distinct difference between these two groups, and it all has to do on for the position of where it is. So a ketone is in the middle. So your carbonyl is in the middle. This is your carbonyl. Is a C double bond O. So when it's in the middle, you are going to have two R groups attached to that central carbon. When it's an aldehyde, aldehyde is an end, you are going to have one R group and it's going to be attached to a hydrogen. Now, if we look into this molecule, we do not see any carbonyls, let alone do we see a ketone. So we know that C is what is not present in Lipitor. But let's continue through the list to hopefully get some more practice on identifying functional groups. Next we have aromatic. An aromatic is something that forms a ring. So ring. And if we notice, we have one here, one here, one here, and one over there. Now we have an amine. So let's draw ourselves an amine, and amine does not have a carbonyl. Amine is just a lone nitrogen attached to R groups. And we have one right over there. And we have a carboxylic acid. A carboxylic acid is drawn like this. Okay. And we have our carboxylic acid right over there. Now, I highly recommend you writing the functional groups on your index card, because it's something that is most definitely going to show up on the exam, and it is something that is going to come up constantly in 321 and if you go on to 322. So let's continue and go down to question number 2. So in this question, you are looking at this carbon over here and this carbon over here. Let's label this carbon 1 and label this carbon 2. And we are going to want to know the hybridization of this carbon and this carbon. So let's look at carbon number 1. Now, to assign hybridization, you are going to want to see how many different atoms or lone pairs your molecule, your atom of interest is attached to. And this carbon over here is attached to one nitrogen and one carbon. So it's attached to two things. So when it's attached to two things, -1, and that gives you an sp hybridized carbon. Now if we look at carbon number 2, it is attached to 1 carbon, 2 carbon, and oxygen, and a little strut in a hydrogen over there. And this is where they are going to try to trick you, is the hydrogen that is not drawn in. So carbon number 2 is attached to 4 things, -1 and sp3. And that is choice number E. Okay, and let us continue. Whoops. And go on to question number 3. And again, this is going to be something that I recommend writing on your card. It is the geometrical shapes. So let's look at labeled 1. It is attached to 1 carbon, another carbon, an oxygen, and that hidden hydrogen that we've been talking about. And when it's attached to 4 different atoms, it is going to be tetrahedral in shape. So let's take out these choices. So now we're left with A and D. Now, here, do you guys know what that is? That is your carboxylic acid. Just a nifty little fact. And on this oxygen of interest, you're going to have 2 lone pairs. So this oxygen is going to be attached to 2 atoms and 2 lone pairs, giving it a bent structure. I hope you guys are all following me. Okay. And let's go on to the next question is from chapter 3, which I have been informed is not going to be on the exam, so we shall skip that one and go on to question number 5, which has to do with resonance stability. Now, what do we know about resonance stability? One of the key components that we know about resonance that is very important to remember is resonance is not showing different molecules, but rather the same molecule. All of these different structures are going to be incorporated into the molecule at any given time. And we are going to want to arrange it with respect to increasing importance. So that means which one is the best resonance structure. Now, first off, let's look at the number of covalent bonds. Actually, that's not a really good way to look at it. Let's look at charge separation. Now, we see that both 2 and 3 have charges on different atoms, but 1 does not have a charge. So that is going to be the most stable. Now, to determine between the stability of choice 2 and choice 3, we're going to go into a rule that I'm sure your professors and your TAs have beat into your head, and that is, do not give carbon a charge. And that is a very, very important rule when you are given the choice between giving oxygen a charge and carbon a charge. Always, 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 always give oxygen a charge, always give nitrogen a charge. Try your hardest to never give carbon a charge, because that is going to be a very, very unstable structure. And we see you have a positive charge on that carbon, so that is going to be the least stable. So 5 is going to be E. And let's continue down into question number 6. And again, we have a question that involves resonance. And resonance, as we said, is very important. And here we are going to draw the different resonance structures. And one of the main things that you want to look for when you're drawing a resonance structure is if you have any lone pairs, because when you draw a resonance structure, you cannot change the connectivity of the molecules, and you could only change where the electrons are. So here we are going to look at these electrons over there, and we're going to bring those down and bring that down and give those lone pairs to that nitrogen, giving it a negative charge. Now this again is very important. When you draw your resonance structures, please do not forget to write the formal charge for your molecule. And I know another of my fellow TAs has put up a formal charge instructional video. You could find the link on the Howler page. And that molecule is over here. So let's look at the other ones. If you look over here, this changed the connectivity. You had a hydrogen here, but you no longer have a hydrogen here. So this is not a resonance structure because you are lacking a hydrogen. And this is not a resonance structure because they added a hydrogen. So your only choice then is 3, so that gives you C. This, I do not think you would be tested on it, but let's go over it anyways, just in case. Now, this is called a deuterium exchange. Whenever you see these reactants, you are going to be exchanging acidic hydrogens with Ds. Now, what do we know about acidic hydrogens? Acidic hydrogens are usually attached to the alpha carbon of a carbonyl or an ester. Yes, yeah, carbonyl or an ester. And if we look here, we have 3 acidic hydrogens. So you know that these 3 hydrogens are going to be replaced. So which one of these replaces those hydrogens? Now let's look at the difference between this one and this one. In choice number F, they replaced all of the hydrogens in the molecule. And one of the main things to take away from this question is a hydrogen that is directly attached to the carbon of the carbonyl is not acidic because you cannot remove this hydrogen. It is going to form a very unstable molecule. These hydrogens are not attached to the carbon directly attached, but rather to the second carbon. So carbon 1, carbon 2. So these are not acidic hydrogens. The only acidic hydrogens are over there, so your choice is B. Okay. What is this question? Okay, now let's look over here. And it says the reaction shown below gives 2 isomeric products. One is shown. Choose the other structure. Now, this also plays into acid and bases, which is chapter 3. So I am almost certain that you do not need to know this, so we shall skip over it. Okay. Now here is something that should have been gone over with you multiple times in the chemistry classes that you have taken, and you are basically going to do to find the overall energy difference products minus reactants, and that is this line here subtracted by that line there, and that difference is C. And this over here is organolithiums, which are going to be covered in a later chapter. So I honestly do not think that this is going to be tested on. This is a synthesis, which is going to be covered later on after your first exam. Later on after your first exam. Okay. Now here are relevant to your exam, but this one is relevant, and I think this is actually the last question that we are going to go over. And here we go. Now this is some more resonance practice, and we are going to look at the lone pairs. So we could either resonate this, or we could resonate those lone pairs, or we can resonate the pi bonded electrons. And and we are going to bring these electrons up and put that on carbon, and we shall get now let us assign our formal charges. Now since this carbon was neutral and it is now getting an electron pair, shall be positive, and this oxygen shall be negative, and this oxygen here shall be positive. Now for the next resonance structure, we are also going to be resonating these lone pairs, and make sure you draw your arrows. Makes it a lot easier to keep track of where your electrons are going in your final structure. Okay. That's it, and we are going to give this positive charge. And it says choose a ketone that is more stabilized by electron delocalization. And when you compare the resonance structures together, not only does this give a better resonance structure by not having a charge on a carbon, but it also has something called conjugation, which you will learn about later on in your organic chemistry career. So this is going to be the better resonance structure.